Okay, so span, lecture 8. What's definition of examples? Linear independence of the span. So the span of a set of vectors is all the linear combinations of those vectors. If we just have one vector in 2 dimensions, it's not too bad. So the span of 1, 2 is all vectors of the form some constant times 1, 2. 1, 1, 2, that's there. There's our vector. What are all constant times 1, 2? Well, if I multiply by positive constants, I get vectors stretched out like that. If I multiply by positive constants less than 1, I get vectors in here. If I multiply by negative constants, I get vectors out here. So the span is a line, right, through the origin. Okay, so what's the span of W1 and W2? So we'll draw W1 is 1, 1, 2, like that. Minus 2, 2, 1, 2, minus 2, 2. So what's the span of that? Well, the span of W1 is all of this. So we'll call that KW1, that's the span, K1. The span of W2 is all multiples of a W2, that's this line. So the span of W1 and W2, span of the two vectors, W1, W2, is all K1, V1 plus K2, V2. So what that means is that take any vector along this line and any vector along this line, say like this, and then if I add them together, then that vector is in the span. But how do I add them together? Well, I come down here and I draw a line parallel to the line determined by W1. So I'll draw a line like this. I come out to this vector and I draw a line parallel to W2 like that, and then that's the addition, right? So if I take this vector here and this vector here and add them together, I get this one. So you can see, if you think about it a little bit, right, no matter what point I pick in the plane, say like that one, I can always find two vectors, one that lies along this line and one that lies along this line, that add up to give me the vector that ends at this point, right? Because if I want a vector that ends at this point, I just take a line parallel to W1, for example, that goes through this point, something like this. And then this vector is a vector K2, W2, and then that vector is a vector K1, W1 that gives me the point that I want. So the span is all vectors in the plane. And so we can go back to the GeoGebra diagram that we had earlier, which is like this. And we can say, let me just turn some of these things off, right? I'll turn that one off too. So there's C and B, two vectors in the plane. There's a line through B and a line through C. And then the span is, if I can take any vector along the red line, any vector along the blue line, and add them up, what can I get? So if I pick some point again, some point D that's just out in the plane somewhere, I can say, well, I want to know, can I take a vector along the red line and a vector along the black line and add them together to get to point D? And sure, there's a vector along the black line whose tip is here, and I can add a vector parallel to the red line to get the vector D. So here's a vector K1, W1, and here's a vector K2, W2 that gives me D. And no matter where I go in the plane, I can get that. And interestingly enough, if I'm up here, if D is up in this upper quadrant, then both K1 and K2 are positive. From down here, the black vector is opposite to its original direction. And so that K2 is negative, but this K2 for the red vector is positive. We're down here, both the K1 for the black vector and the K2 for the red vector are negative. And out here, black vector is multiplied by a positive constant, but the red vector is multiplied by a negative constant. And, you know, we could have gone the other way as well, right? Set it up like that. So any vector in the plane is actually a linear combination of those two. And when that happens, we say the span of the two vectors, the black vector and the red vector, is the entire plane. Okay, so back to the notes. Okay, so why is the span of W1, W2, and W3 the same? Shows that the span of should be here is the same as the span of W1, W2. Well, we already know that W1, W2 so in particular, W3 is equal to something times W1 plus something times W2. And I had that written down here somewhere, what that was. No, I can't find it. So, okay, so in fact, K1 turns out to be 5/3 and K2 turns out to be minus 7/6. Right? How do you find that? Oh, this equation becomes 1, 2, minus 2, 2, 4, 1. And this is K1, this is K2. So if I want to solve this vector equation, I can solve that by setting up a vector whose columns are W1 and W2, those two vectors, and whose right-hand side is the vector W3. So this is W1, this is W2, this is W3. Reduce it to solve for K1 and K2, and you get that. So span of W1, W2, and W3 is all vectors of a particular form. K1 V W1 plus K2 W2 plus K3 W3. But W3 we know is 5/3 W1 minus 7/6 W2. So span of W1, W2, W3 is all things of form K1 W1 plus K2 W2 plus K3 times this 5/3 W1 minus 7/6 W2. Or finally, K1 plus K3 times 5/3 W1 plus K2 minus 7/6 K3 W2, which means that the linear combinations of W1, W2, and W3 are actually just all linear combinations of W1 and W2. So the span of W1, W2, W3 is all linear combinations of W1, W2, and W3. But since we know that W3 already is a linear combination of W1 and W2, we can eliminate W3 and just say that the span of W1, W2, W3 is just the span of W1 and W2. So here are two vectors. What does this look like? Well, it's hard to draw because this is kind of in 3 dimensions. This is my X coordinate, this is my Y coordinate, this is my Z coordinate. So there'll be 2 in the X direction, -1 in the Y direction, X, Y, Z, and then 3 in 2, -1, and then 3. So there's more or less V1. And then V2 is -5, and then -2 in the Y direction. So that takes me out to about here, and then 6 in the Z direction. So it's actually quite tall. So that's V2. So the span of the vectors is all linear combinations which is all things of those types. Now we know that K1, V1, the span of that, if we just let K1 vary, that just gives us this line in 3-dimensional space. K2, V2, if we let that vary, that just gives us this line in space. So K1, V1 is a line in space, K2, V2 is a line in space. If we take vectors on this line plus vectors in this line, what we get is we get the plane in space defined by those 2 lines, defined by V1 and V2. So if you have any plane, if you have 2 lines in space, they define a plane, the plane that's sort of, you know, they're on. So here's another picture of this. Hopefully this is going to work. Here we go. That looks a little messy. Oh, and it's not working. Sad that GeoGebra is unreliable sometimes. Well, the 3D demonstration crashed. So I'll try and set that up separately and do a little 3D thing there. But you get a plane in 2 dimensions, right? 2 vectors gives you a 2-dimensional plane in 3 dimensions. So linear independence and span, if you're given a set of vectors, you can throw out vectors until you get a linearly independent set. So if you remember from the example above, we had W1, W2, and W3. And the span, since W3 was a linear combination of W1 and W2, the span of the 3 vectors together was just the same thing as the span of W1 and W2. So if we have a bunch of vectors, if they're not linearly independent, then that means if they're not linearly independent, you can pick one of them, say V1, and that'll be equal to a linear combination of the others. So the span of the set V1 through Vn is everything, all linear combinations, K1 V1 plus ... plus Kn Vn. But if K1 Vn, if this is a linear combination, if V1 equals some linear combination, should use different letters. So we'll call this M2 up to Mn. What happens to my linear combinations? Well, they just become, we just replace the K1 V1 with this. And so our linear combinations becomes K1 M2 times V2 plus K1 M3 times V3 plus dot 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 plus K1 M sub n V sub n plus K2 V2 plus dot 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 plus Kn V sub n. And this is a linear combination just of V2 through Vn. So if we have a linear dependent set, we can always just throw out vectors and we will not lose anything from the span. The problem is that if we have a linearly independent set, right, then if we throw out one of the vectors, so if we throw V1 out of this set, then the span is not the same. So here, you cannot write any of the vectors like V1 as a linear combination of the other vectors. And why is that? The only solution is linearly independent to this is K1 equals 0, K2 equals 0, dot, 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 Kn equals 0. If V1 is a linear combination of the others, that would mean that we could write an equation K1 V1 plus K2 V2 plus dot, dot, dot with K1 equal to -1. And then that it contradicts linear independence. So in particular, V1 is in the span of V1, V2, dot, 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 Vn, because V1 equals 1 times V1 plus 0 times V2 plus dot, 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 plus 0 times Vn. So it's a linear combination of those, but V1 is not in the span of V2 through Vn. And in a sense, it's sort of the best thing we can do. If we want to know what a span is, we want to find a linear independent set that has that span.